Particle Physics 2008 Higher Level Question 10a. So as always, we're going to start by marking off all of the different types of questions here in our exam question. So we're going to say baryons and mesons are made up of quarks, and we have to list the fundamental forces. So that's going to be part 1. To name 3 positively charged quarks, so that's another one, so that's part 2. What's the difference in the quark composition? Part 3. What's the quark composition of a proton? Part 4. After the collision, 3 pions are admitted. What's the net charge? And justify our answer. Part 5. Part 6, we have to calculate. Now, obviously, we have part 1 and part 2 there. So, I mean, you might have preferred to call these A, B, C, and D. That's up to yourselves. So we have a subpart in part 6, 2 parts to it. Okay, and also something important to note here is this time we're actually given the charges of the electron, the mass of the proton, mass of pion, and speed of light. So rather than having to refer to our maths tables, page 47 and 48, we're given the values. So if you're given the values in these questions, you use the values given to you. Would be the best approach for these questions. Okay, so let's look at the first question then. So the first question says, baryons and mesons are made up of quarks and experience the 4 fundamental forces of nature. So we have to list the 4 fundamental forces and we have to state the range of each one. So we're not having to put them in any order or anything like that this time. We are just stating the fundamental forces and then identifying the range. So if we go to page 374 in your textbook, or if you refer to your notes in your PowerPoint, then you can have your table there that are comparing your fundamental forces of nature. All right, so our first one is our strong nuclear force. And its range then is only a short range, right? Because it's obviously only acting on what's inside the nucleus. So let me write short range rather than range. So short range. So it's acting on the materials inside the nucleus. The next one we have then is the electromagnetic. And our electromagnetic force is infinite. We then also have the weak nuclear force. And our weak nuclear force has a short range. So it's always occurring in beta decay. And then our last one is obviously our gravitational. And obviously this is acting on galaxies and planets, so it's an infinite range also. Okay, so basically what we have there then is 2, 4, 6, 8 marks in total for this question. So it was basically 2. So stating the force and stating the range in each case. So you're getting 1. So it was 1 for the strong nuclear force, 1 for the short range, 1 for electromagnetic force, 1 for inert range, etc. Okay, so we have 2, 4, 6, and then 8 in total. Okay, so part 2 then says name 3 positively charged quarks. Okay, so again, if we go to our quarks, which is page 49 in your maths tables, and in your maths tables, obviously you can see we have up, strange, top, down, charmed, and bottom. So we have to list 3 of them, and they have to be positive. And obviously then if we look at that table, we can see up has a charge of 2/3, whereas strange has a charge of -1/3. So therefore we're only going for the ones that have a positive charge. So that would be up, and then top also has a charge of 2/3, and then charmed also has a charge of 2/3. So all of those have a positive charge. Okay, so then what are the marks for that? So again, it was 6 in total. So if you didn't get all 3 right, it was breaking down into 2, 2, and 2. So 2 for each correct answer. Part 3 then says, what's the difference in quark composition of a baryon and a meson? So if we're looking at our baryons, Well, our baryons are made up of 3 quarks. As opposed to an antibaryon would be made up of 3 antiquarks. And then a meson are made up of 1 quark and an antiquark. And they don't have to obviously be the antiparticle of the other, okay? So it can be an up and an anti down in your composition. So part 4 then, what's the quark composition of a proton? So you need to know these off by heart, because obviously you can't get anything in your tables that's going to help you other than the fact that we know the proton is +1 of a charge. So therefore we know that the quark composition must amount to a positive charge of 1. So of course the quark composition of the proton is up, up, down. And again, if you go to your tables, page 49, you'll see up is 2/3, plus 2/3 would be 4/3, and then take away a down, which would be -1/3, which gives us an overall positive charge of +1. So the proton is up, up, down. So it was 3 marks for that question. And then the baryons and the mesons was also 3 marks and 3 marks. Okay. All right, so the next one then is part 5, right? So we have a circular particle accelerator, and we have 2 protons injected into the accelerator, and they're each given a kinetic energy of 1 giga electron volts, and they travel in opposite directions and then they collide. So we're told after the collision, 2 protons and 3 pions are emitted. Okay, so a bit like when we were looking at the question in 2011, we only had 2 pions produced in that case. This time we have 3 pions. So depending on the speed of the colliding protons, that's going to determine what happens after the collision. So the first thing we're asked here is, what is the net charge of the 3 pions? And we have to justify our answer. Okay, so let's have a look. Well, let's write out the equation. So we have a proton and a proton colliding. And after that collision, we have our proton and our proton. And then we have 3 pions. Now we need to know is, what must be the net charge of these 3 protons? So what's the charge? Okay, and it only wants the net charge. Okay, well, if we look at the proton has a charge of +1 and another charge of +1, and after we have a charge of +1 and we have a charge of +1, and therefore we have a total charge beforehand of +2 and a total charge after of +2. So therefore the net charge of these 3 pions has to be 0 in order for our charge to be conserved in this particle collision. So obviously we could have 3 neutral pions, or we could have a neutral pion, a positive pion, and a negative pion, and therefore the net charge would be 0. So we don't need to state what each of the individual ones are, but we have to be able to justify our answer. So we say, i.e., the net charge of the 3 pions is 0, as charge must be conserved. Okay, so we had 6 marks for saying 0, and then 3 marks for justifying our answer, so that the charge has to be conserved. Okay, so part 6 then. So part 6 is our calculation. So we're looking for the combined kinetic energy of the particles after the collision. And then also we're going to look for the maximum number of pions that could have been created during the collision. So we're told 3 pions are emitted, but they're asking us, well, how many is in total could have been possible based on the kinetic energy of the 2 colliding protons. Okay, so let's have a look. So what we have then is our energy before must equal the energy after, because we know we have conservation of energy. And the energy beforehand, we're told, is that each proton is given a kinetic energy of 1 giga-electron-volts. So therefore the energy beforehand is going to be equal to 2 giga-electron-volts. And of course giga is, if we go to our maths tables, is going to be 10 to the power of 9, which is page 45 in your maths tables. Okay, so then our energy after. Alright, well this basically is going to be the energy mass equivalent. So in other words, we're going to have the energy of the colliding protons is going to be used to make the 3 pions. And then anything left over is the kinetic energy. Okay, so you could either have all of that 2 by 10 to the power of 9 electron volts be used to make as many pions as possible, or it can be used to make the 3 pions, and anything left over then is used for kinetic energy for the particles. So what we need to do is we're looking for, in this question, the combined kinetic energy of the particles after the collision. So we're looking for this leftover energy. So basically all we have to do then is to get the energy before minus the energy needed to make the 3 pions, and the difference between the two must be the kinetic energy. So let's look at how we're going to find the energy to make the 3 pions. So using Einstein's E equals mc squared, well, what we have is the energy is going to be 3 pions, so it's going to be 3 times the mass of 1 pion. And we're told in the question that the mass of a pion down here at the bottom is 2.4842. So 2.4842 by 10 to the power of minus 28. And then that's times the speed of light squared. And again, we're given the value for the speed of light here, so we're not using our tables, and we're not using 3 by 10 to the power of 8. We're using 2.9979. So 2.9979 2.9979 by 10 to the power of 8, and that's squared. Okay, so the energy needed to make the 3 pions then is 6.697 953.011 by 10 to the power of minus 11, and that's joules. So of course, because if we go back to the previous page here, we have our energy beforehand is in electron volts, then we need to make sure that we're dealing with the same units for comparison. So I need to convert this to electron volts. So of course, remember, when we're converting to electron volts, we take our energy and we divide by 1 electron volt, which is the charge on the electron. And again, we don't need to go to our maths tables for this either, because we were given that, and the charge on the electron we have to take here to be the rounded version of 1.6022 by 10 to the power of minus 19 coulombs. Okay, so that gives us then the energy needed to make the 3 pions in electron volts to be, so 418,047,248.2 electron volts. So in other words, that's 4.18. What did we have our electron volts into? So 4.180472482 by 10 to the power of 8 electron volts. Okay. So that's the energy for our 3 pions. So then the difference is going to equal the kinetic energy. So therefore the combined kinetic energy is going to be 2 by 10 to the power of 9 electron volts minus 4.18047 2482 by 10 to the power of 8. And therefore that gives us kinetic energy of, combined kinetic energy I should say, for all of the particles to be, so 1.581952752, and that's by 10 to the power of 9 electron volts. So all of that is the leftover energy after the pions have been made, and therefore will be used as kinetic energy. So therefore we had 3 for using our E equals mc squared. We had 3 for multiplying it out, getting it in joules, and then getting it in electron volts. And then we had 3 for getting it for the 3 pions, which I've already done obviously at the start. So essentially there was 6 for using your E equals mc squared and then multiplying it by 3. And then we had 3 for getting the difference between the two. So in other words, 18 marks in total for that question. Okay, so the last bit then, what have I called that? So that's the first part, okay. That's part 1 essentially, as they have referred to it as. And the next bit is we have to find the maximum number of pions that could have been created during the collision. So in other words, if this energy here is not used as kinetic energy, it could have been in fact used to make more particles. So all we need to do is look at this leftover energy and see, well, how many pions could we have gotten out of this leftover energy? Okay, so the number of pions, okay, so it would be the energy, which we said was 1.581.952.752 by 10 to the power of, 9. Now that's in electron volts. So of course if I'm dividing that by the mass of a pion, then the mass of the pion, again here, is in kilograms, right? Sorry, not the mass of the pion. The energy needed to make 1 pion was here. Okay, so we have the energy needed to make 3 pions. So if I take this number here, the energy needed to make 3 pions, and I divide that by 3, I can find out the energy needed to make 1 pion. Okay, so we do this to the side. Energy of 1 pion. Okay, so that's going to be 4.10 10847 472482 by 10 to the power of 8. So that's the energy of 3. So if I divide that by 3, that gives me, sorry, I've actually written that number down wrong. I'll just go back. So if we go back, it's 41804. So 418047 2482 by 10 to the power of 8. And then so that's the energy in electron volts to make 3. So if I divide that by 3, then that gives me 1.393490827 by 10 to the power of 8, and that's electron volts. Okay, so that's the energy needed to make 1 pion. So we have all this extra leftover energy that was used for kinetic energy in part 1 of the question, but now we want to know is if that's not used for kinetic energy, and instead we can use all of that energy to make as many pions as possible, well then how many pions are possible? So if I divide that in, then we end up with 11.35, and obviously we can't have a 0.35 of a pion, So therefore, the extra pions would be 11, okay? But that's not what the question asked, so we have to be careful here. Let's go back. It says, what's the maximum number of pions that could have been created during the collision? So that's in total. So we saw that in the collision we had 3 pions emitted. So all the extra leftover energy, if it's converted into just all pions and no kinetic energy, there might be a tiny bit of kinetic energy left over, then what we would have is the 11 plus the 3. So therefore we say total pions made would be 11 plus the 3 already made, which gives us 14 pions in total. So that's the maximum number. Okay. So therefore we had 3 for working out the 11 and 3 for getting our maximum number in total. Okay, so nice question.